Okay, so here is a very high level kind of.
Oh, what is this? So many components now.
Yeah, so
you had only one coil.
So I think I was thinking, maybe we should start with the kind of a high level diagram, how a whole system would look like, and then kind of go back to the search coil and then kind of talk more about how to design such a search coil. But if you look at this, what do you see here?
So I can see kind of a transformer there.
Yes. So this is just a way to look at a system, right, of a search coil. But it's not just a coil, basically. So you can probably see 4 different components here, or modules, right?
Okay.
So here, you can think of this like an electromagnet. This has a
current source?
Current source.
Okay.
Right? Producing.
So you are injecting current through a coil.
Okay. Right? That produces a
magnetic field.
Time varying magnetic field. And here you have your search coil.
Okay.
Okay. And that coil, because of some mutual inductance, right? It's gonna, as we talked about before, induce a voltage. Okay. But if you look at the search coil, you see this L self, R coil, C coil.
Okay.
What are they?
L coil may be the self-inductance of the coil.
Self-inductance. Okay. So now we have another parameter to consider, right? Before it was just the size of the coil and the number of turns. But now, now we have the self-inductance. What about this C of the coil, capacitance?
C of the coil.
Yeah.
Why C? I have not connected any C there.
What about the number of turns? You talked about number of turns. What's going to happen if you increase the number of turns?
So these turns are insulated.
Turns are insulated.
Anyway, it's an insulated wire. True. So you have conductors stacked, and they are insulated each other.
Yes.
So you have if you take 2 turns, this is separated by an insulator.
Yes.
So you have a capacitor. So for an entire coil, maybe we can represent it as a lumped capacitor.
Lumped capacitor. Correct.
Although they are distributed between each turn.
Yes, because you could have number of turns and you could have several layers of that turn.
Correct.
So you could have turns, and then on top of that you could have another layer.
Yes.
You could have many layers.
Yeah.
And then obviously its capacitance comes here.
So that's what you have introduced.
Yes. So that means there's another variable now. Okay, you need to consider. Now there's the self-inductance, as you said, capacitors because of the number of turns, and also,
of course, the wire will have some resistance.
Right? So the wire will have some resistance. Okay, fine. Now, let's say we have both now. Now somehow we need to connect it, right? We need to get the output. Right? So generally, you'll have some sort of a transmission line, like I don't know, a BNC cable or coaxial cable or something like this. And that will get the signal, right? And then it will output it to your, let's say, a data acquisition system. But that transmission line also has
series resistance, again distributed capacitance,
which we see here, right? Here and here. So we need to consider 2.
Correct.
Now, when we get to the final module, which is your data acquisition system, the preamplifier, integrator, whatever it is, the circuit, then you also have certain things to consider. Right? But if I were to ask you this part here, what should be the most important feature or characteristic of this final part? As it has something to do with impedance. We don't want current going back into the coil. So in that case,
so it has to be matched. Impedance matching has to be ensured.
Yes, and it ideally should have some high input impedance in the line.
Yeah.
So this part here, as you said, should be matched, right? And also has high input impedance. Right? So this is basically a very high level view of what a surge coil system would look like. So already now we have a lot of things to consider, right?
Yeah, it's not just a coil.
It's not just a coil. We cannot just wind a coil. Actually, we can wind a coil, and I think we will be able to detect a magnetic field. But then if you're, I think, designing a sophisticated system, there are a lot of other things to consider. Right? Okay. So this coil yoke here, this capacitance, we will not talk about that because at the moment,
I was thinking, what is it? But I couldn't read it. What is it written?
So I think that's coil yoke.
Uh-huh.
Right? So I think if there's something in between, okay, the coil, and let's say something magnetic, for example, there could be some capacitance there. Okay, so that's a high level view. Now, before we, talked about inductance and capacitance, but let's say if we ignore all that, okay, if we ignore all that, and then let's say you have an AC coil. Now this is
the induced voltage.
Induced voltage. Okay, it's voltage. Yes. Now, then you have your R of coil, and then your voltage input, which is going out, right? Now, if you have V in, right, the ratio of V into the V coil, right, then you get something along the lines of R in. I mean, it's something like a voltage divider, right? R coil, right? So then V in is equal to 1 over 1 plus R coil divided by R in. Now, what do you see already? I mean,
there is some division. There is some fraction that's going to.
I know you do not like these fractions. You're always finding methods to get rid of this fraction, right? But you're absolutely right. So already, even if you don't consider the impedance and the capacitance, already your output has this component here. That's going to reduce your voltage output. Exactly. So already we have a problem, right? So in this case, your I coil will be V coil divided by R coil.
So this is even with after you neglecting the self-inductance and the capacitance.
Yes. So even if you neglect that, right, just to
so maybe for a very low frequency of B.
Exactly. For a very low frequency of B, because then you can neglect.
Yeah, omega L will be very small, and 1 by omega C will be very large. Yes, so that we can neglect.
Yes. So in such a situation, but the point is, in such a situation,
and then there is the
got it, right? So now already it's producing, right?
So this R in is the input impedance of something that you are going to use.
Yes, to measure like a preamplifier or as extension system. Yeah, this R in, yes, this part here. Okay, so it seems like it's getting harder and harder. It's coils, more variables. If you look at it a bit closer, then you also see the output somehow is reduced by a 1 plus R coil over R factor.
Yeah.
Any other things you need to?
No, I'm good.
Yeah. Okay, but in reality, we cannot ignore.
Yeah, these guys are there.
These guys are there. So, now if you consider, let's say, an induced voltage due to a okay, so as you said, L is the total inductance of the coil.
Yeah. Self-inductance.
Self-inductance. Let's call it self-inductance. And then C is the
coil capacitance.
Coil capacitance. So that could be due to the number of turns and different layers, right? R is the resistance of the wire.
Yeah. It's written R1 or something?
No. Sorry, yeah. So let's say in this case R1. Yes, resistance of the wire. What's this RD?
RD or R0? It's written RD?
RD. called a damping resistor.
Oh.
Now we are still measuring, of course, the output, right? And that damping resistor, let's say it represents the resistive and the reactance components of the preamplifier. Let's say we have the preamplifier.
Okay, for example.
Now, why do we need this, and what's...
So then it's not just a resistor, it's an impedance.
It's an impedance. It really should be Z, no?
Yeah.
Yeah, really should be Z.
Yeah.
But let's say it's representing
Yeah.
the resistive and the reactance component. But yes, ideally...
It will be dominated by the resistance.
Yes. Yes. But now we know, because there's R, L, and C, there's going to be some resonance.
Possible, yes.
Possible.
Yes.
And do you think this RD can somehow tune the sharpness?
The Q factor can be adjusted.
I mean, we'll talk about all this a bit later on. But generally, I think if you have
higher the RD is better.
Yes.
Right.
If you have high RD, you might get close to your critical damping factor. But then, but again, in reality, this is what you need to consider, right? You cannot just talk about resistor. That was just to show that even if you just have resistor, you're going to decrease your...
So you are going to use that RD to adjust the damping factor.
Yes.
That's why it's called as RD.
RD.
Okay.
Because...
But this is something external. While other three, L, R1 and D are part of the coil itself.
Yes. This part is the surge coil.
Surge coil.
But because we have R, L, and C, right? We won't get, our output, right?
Yeah.
We'll have some resonance.
Yes. Because of this. The voltage V1,
VI, the induced
VI itself is a function of the frequency of the flux density.
Yes, that's the time varying flux density that is measuring.
Yeah. Now, on top of that, now this RLC is also something depends on the frequency.
Yes, exactly, right? Your reactances.
Correct.
So then you'll somehow need an external, right, way to control the output or the outcome of this circuit, which is why you have something.
So if I simply measure the output voltage, I may not get a correct value of BM like you mentioned earlier.
Exactly.
Right.
It's not that simple.
Yes. Because it's now, it depends on at what frequency as a function of the circuit elements. Earlier expression assumed that the C is not present.
Or even L is not.
At least if the C is not present, then there is no current flow.
Yes.
If RD is also not there, then maybe it is fine.
Yes. But in reality,
all these are there.
And we cannot ignore them when we're designing a surge coil. You also mentioned...
this may... Sorry.
No, go ahead.
So this may decide the bandwidth also.
Yes, that's exactly what I was going to say. So you mentioned the frequency, right? So if you have a frequency range, right, and you check the output, right, by designing these factors correctly, you might be able to design a surge coil to work within a frequency
that we are interested
in, right? Or what the use case or the application requires, right? So that's why it's important to consider all these different things when you're designing a surge coil. Now, Bobby, you talk about the frequency response, right? Now that's limited by the ratio of L to R. Right? So basically the time taken for what? The induced current to dissipate when B disappears. Okay? So that frequency, that's the limitation of this one. Now, if you have a high L, inductance. Your I or your current going around circuit, dissipate is what DIS, dissipate slower. Yeah. Now, if you have a low R, it will dissipate faster.
Yeah.
Right? Just some basic things that you can.
This is
get from
applicable for any LR circuit.
This is applicable for any LR circuit. Yes. Yes. I mean, C doesn't really matter in this case, right? But if you're talking about frequency response, then you talk about L. Are there any cases where we need to take C into account?
C, we will have to take into account, I think. But maybe here, when you compare with C and RD, maybe RD is more dominant.
Yes.
It all depends on the values of these components and the frequency that you are interested.
Right. And you already saw that before. You said ideally this should be high, no?
Yeah, correct.
So that's correct, right? So if this is high, then maybe you can get rid of this, get rid of the influence of C. Okay.